Imagine this glowing curve describes energy near a resting object. Its bends matter, but the full shape is awkward to calculate with. Could we rebuild it from simpler pieces? A level, a tilt, a bowl, and higher powers. Power series replace that difficult shape with polynomial pieces we can calculate, draw, differentiate, and combine. We met this idea in the geometric series. Remember the point approaching a wall by crossing half the remaining gap each time. Its distances were 1/2, 1/4, 1/8, and onward. Every finite partial sum stopped short, while the sums settled toward 1. Infinitely many shrinking contributions produced one number. Now, instead of fixing the ratio, call it the variable x. Move an x slider. For each input, add 1 plus x squared and onward. When the terms settle, place the result above that input. Sweep the slider and the points trace a function, g of x equals 1 over 1 minus x, where the absolute value of x is less than 1. A series can build a curve, not just a number. The geometric example gives every power the same weight. Separate it into 1, x squared, x cubed, and onward. These powers are our building pieces. Notice their roles. 1 sets level, x supplies direction, and x squared introduces bending. Equal weights force one curve. To build other shapes, we need independent control over each piece. Put a coefficient before every layer. The first raises or lowers the flat layer. The next tilts. Another controls the bowl. Stretch a coefficient and its layer strengthens. Change its sign and the layer flips. Set it to 0 and the layer vanishes. No layer replaces another. At every input, their heights add into one output. The weighted layers combine point by point into the sum of a sub n times x to the n. How can we calculate infinitely many layers? Use the same finite first idea as before. Turn an n dial to 0 and keep the constant. At 1, include the linear term. At 2, add the quadratic term. Every setting produces an ordinary polynomial, p sub n, that we can evaluate immediately. The newest term stays amber, making each improvement visible and showing what extra calculation buys us. Increasing n reveals whether the approximations improve. We gained flexibility, but created a new problem. With endlessly many coefficients, which ones reproduce the target curve? Instead of guessing, place a measurement scanner at a chosen center, x equals 0. Derivatives separate these powers at the center. The scanner will examine the target locally, one feature at a time, and convert those measurements into coefficients. First, measure height. At the center, every positive power of x becomes 0, leaving only the constant. Choose a sub-0 to equal f of 0. The polynomial and target now pass through the same point. We have matched where the curve begins, but not which way it moves. Next, measure slope. The constant contributes none. At the center, the linear layer contributes exactly a sub-1, while higher powers remain flat. Set a sub-1 equal to f prime of 0. The approximation rotates until its tangent matches the target. Now they share height and direction. Height and slope cannot describe bending, so scan curvature with the second derivative. Differentiate x squared once, and it becomes 2x. Again, and it becomes 2. The quadratic layer therefore contributes 2 times a sub-2 at the center. To match the target, a sub-2 is f double prime of 0 divided by 2 factorial. The factorial corrects the multiplier created by repeated differentiation. The pattern continues. Differentiate x to the n repeatedly. Each pass lowers the power and pulls down a number, n, then n minus 1, and onward. After n passes, the multiplier is n factorial. Every lower power has disappeared. One derivative measurement can isolate one coefficient. In general, a sub n equals the nth derivative of f at 0, divided by n factorial. This is the Taylor series centered at 0. Test the recipe on the exponential curve, e to the x. Differentiate it once, twice, or any number of times, and the same exponential returns. At 0, every derivative equals 1. Its coefficients are therefore 1 over n factorial, giving 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and onward. Watch the finite approximations work. P sub 0 is a line at 1. P sub 1 adds the tangent. P sub 2 bends, then the cubic through 6 terms join. Each amber term changes the cyan approximation, which hugs the cream exponential across a wider interval. Higher terms widen the useful interval by correcting differences there. We never calculate infinity at once. We calculate useful polynomials and watch their agreement grow. One warning completes the idea. Matching derivatives at the center gives a candidate series, but does that guarantee behavior everywhere? No. Agreement depends on the input. We need only see the convergence question. Probe 2 inputs. At x equals 0.7, terms shrink and partial sums settle toward 1 over 1 minus x. This is inside the interval. At x equals 1.1, terms grow and partial sums escape. That is outside. The coefficients succeed here and fail there. Paint inputs green. For the geometric series, agreement means the absolute value of x is less than 1. Taylor coefficients select the pieces. Convergence determines where their sum represents the function. A pattern is not permission to use the series everywhere. Now return to the energy landscape and zoom into its minimum. At the bottom, the horizontal tangent means the first derivative vanishes. The constant shifts energy. The leading shape is quadratic, 1/2 v double prime times x minus x0 squared. Curve and bowl become indistinguishable. That bowl is the harmonic-oscillator model, a gateway to vibrations and quantum mechanics. Power series give us 3 tools: polynomial pieces, derivative-chosen Taylor weights, and an agreement region. Together, they replace difficult functions with finite approximations, preparing us for waves and quantum mechanics. That is what the method solves and why it matters.